Now, Hall voltage is a new addition to your syllabus. Okay, Hall voltage is a new addition to your syllabus. You only see Hall voltage or Hall effect from 2016 onwards. Okay, 2016 was where they changed the syllabus. They made some revision to the syllabus, so they added Hall effect from 20. They added Hall effect during the revision here. Okay, so when it comes to Hall voltage questions, you won't see it before 2016, only from 2016 onwards. Okay, so now what is actually Hall effect or what is actually Hall probe? Wait, there are some things I just need to write here first. Now, in real life, you want to measure how strong is the magnetic flux density or magnetic field strength of a certain object. Okay, so what we'll tell you is that to measure magnetic flux density or magnetic field strength, we use a particular device called a Hall probe. Okay, to measure magnetic flux density, a Hall probe is used. Okay, a Hall probe makes use of Hall effect that produces Hall voltage. Okay, that produces Hall voltage, VH. Okay, you want to measure the magnetic flux density, we make use of something called a Hall probe. So a Hall probe makes use of Hall effect that gives us Hall voltage. Now, Hall voltage is a measure of B, because we will show you later on that VH is proportional to B. Okay, so how does your Hall probe looks like? It looks something like this. Wait, I'm trying to Google image search the thing. Yeah, it looks something like this. Right, now I think you should be able to see this screen here. Your Hall probe looks something like this. Okay, there's this little green tip here connected to a meter here. This little green tip here is your Hall probe. Okay, you will move it around some place where you want to measure the magnetic flux density, and inside the so when you go and poke it around somewhere where you want to measure the magnetic flux density, it will make use of the Hall effect to give you a Hall voltage. That Hall voltage is displayed here, which you can then convert to magnetic flux density. It will tell you how strong the magnetic flux density is at the place where you're measuring. Okay, so your Hall probe here actually has a slice of material, a rectangular slice of material that looks like this. Okay, that Hall probe, the tip of the Hall probe has a rectangular slice of material that looks like this, which can be made out of conductor, which can be made out of semiconductor. But say for example, right now we just consider this slice as a conductor first. What you do is that Hall probe containing this slice, you place that slice perpendicular to your magnetic field. Okay, you place it perpendicular to your magnetic field here, and then you run current through that slice of material. Say your current is now going from here to here, like this. This is your I, and then this is your B going downwards, like this. So, what do you expect to see happening? Now, this I here you can assume as flow of conventional current. So that means it is flow of positive charges. So you consider what happens first when you have a positive charge that moves in. Consider the first positive charge that moves in first. This is the first positive charge that moves in first. If you use your Fleming's left-hand rule, again I draw the Fleming's left-hand rule, where this one is FB, this one is B, and this one is I. Your magnetic field is going downwards, your current is going towards the right. You will see that your magnetic force is going to be in this general direction. So what will happen is that if your first charged particle comes in, it experiences a magnetic force. That magnetic force will cause this charged particle to move towards this side. Okay, it will cause it to move towards this face of your slice. I mean, this one here, if I try to draw it in 3D, you see that there is something like another face here like this, right? Isn't it? So there's a face here. So this first charge particle that comes in, it will be deflected here. It will be pushed towards this face. Okay. Now, because this thing is charged, carrying a positive charge, when you push it to one face here, it's going to cause this face to become positively charged. So your face here gains positive charge. But on the other hand, the other face here will become negative charge. Okay. So when you push your positive charge here towards this face, you're going to cause this face to become charged. This face here will become positive. This face here will become negative. So what happens then if you have another second charge that comes in? For the second charge that comes in, say this one, this is your second charge that comes in, it still experiences the same magnetic force as before, but now there's another different force acting on it. Because this side is now positive, this side is now negative, your charged particle here is going to experience an electric force. Electric force in this side, in the opposite direction to your magnetic force. How do I know that? Is your positive plate will repel the positive charge, your negative face will attract your positive charge, so your Fe in general is this side. Or you can also think of it as this way lah. Here is positive, here is negative. The direction, if you have this side positive, this side negative, you actually now have potential difference here. You actually have an electric field already, and the direction of your electric field is going from positive to negative here. The direction of electric field is here. So if this is a positive charge, your direction of force on a positive charge follows direction of your electric field. So you know that it's going to be here. So now, when your second positive charge comes in, you're going to experience magnetic force and electric force, but your electric force here is weak. It is not that large. You will have a case where your FB is still larger than your FE. So what would then happen is that this second positive charge now gets deposited here, causing this face to become more positive. So your PD across here becomes even larger. So what happens then is that if you have another third positive charge that comes in, you still have magnetic force, but you also have electric force here. But this electric force is larger than before. Because now you have more charges here, your electric force that you experience is going to be larger. But assuming that your FB is still larger than your FE, this third positive charge will again still be deposited on this face, causing this face to become even more positive. There's a larger potential difference across this face. There's an even larger electric field. So when you have a 4 positive charge, 5 positive charge, 6 positive charge, 7 positive charge, and so on and so forth, this process will keep repeating itself. So the process will repeat itself where you see your Fe will keep increasing. So this process will continue until such a point where your Fe increases to the point where it's equals to your Fb. So at a certain point, if you let the process keep running, there will be one particular point where your Fb and Fe are equal and opposite. At that point here, your charged particle will just move straight through. Okay, so your charged particles moving straight through here would mean that you have achieved Hall effect already. Okay, so Hall effect is kind of like this. Hall effect is where you have maximum accumulation of charge on the faces of the slice. This one, the charged particles are no longer deflected to the faces, but move straight. So at this point, there is max PD across the face. This is the Hall voltage. Okay, this is the Hall voltage. So your process here is this: you want the charged particles to come in. Initially, the charged particles will be deflected toward one face of your slice. So the process will continue until such a point where your charged particles will move straight. Okay, when the charged particle moves straight, your Fe and Fb are equal and opposite to each other. You no longer have any accumulation of charges on the faces. This is where you already have maximum accumulation of charges. The charged particles no longer no longer get deflected, they move straight through. So at this point here, when you have maximum accumulation of charges, the PD across here, these two faces, is maximum. That is what you call as your Hall voltage here. Okay. So this is your Hall effect that gives you your Hall voltage. So when you have Hall voltage, you have maximum PD between the faces, and this is established when force on the charged particle due to Fb, due to magnetic field, is balanced by the opposite directed force due to electric field between X and Y. Okay, this is where you have Hall voltage here. Is when your charged particles move straight through. Now, just now I mentioned to you that your Hall voltage is a measure of your magnetic flux density. How do I know that? Is what you know happens during Hall voltage. Once you've achieved Hall voltage, the charged particles move straight, where Fe is equals to Fb. So Fe is QE, Fb is BQV. So you have this equation here, but then you want to sort out for E. Now when you want to sort out for E, you know that E is your field strength. You can actually sort out E as E equals to VH over D. Now you see just now that there is this phase that will become positively charged, and then there's this phase that will become negatively charged, right? Now if you look at it exactly from the top like this, it's like you have charged parallel plates already, where this side is positive, this side is negative, and then it's separated by distance d, and you have a PD across them. So in your AS electric field, you know that electric field strength is V over D, right, for charged parallel plates. So these phases which now carry charge is akin to charged parallel plates, where your PD divided by the distance will give you your electric field strength. So I can say now the E here can be represented by the Hall voltage divided by the distance between the charge faces. Okay, so that's why I can say E is equals to VH over D. So then this sub inside here, I'll get this. VH over D is equals to BV. Okay, so eventually you rearrange it, you get VH is equals to BVD. So you see now, this one is clearly showing you that VH is proportional to B. That's why I mentioned to you just now, Hall voltage is a measure of your flux density. The higher Hall voltage you have, the higher your flux density. Okay, it's a measure of your flux density or your magnetic field strength. But this one is not enough. Okay, you want to expand it further until you get this expression for Hall voltage. Now, the derivation of Hall voltage in this form is required in your syllabus. That's why I wrote it inside here. The derivation is required. You need to know how to derive the Hall voltage. There's usually two stages to the derivation of your Hall voltage. The first stage is this one. Okay, how do you derive it to this one from here to here involves the second stage, which is this one. Now, if you look at your equation here, and then the final equation you want here, you notice that you no longer have the expression for V. V has disappeared from your equation. So, and then after that, you have an expression for N. N here is not number of moles or anything like that. This one, N here, relates to what you learn in your current electricity or AS, your number density. Remember in AS electric field, we told you I is equals to ANQV or NAVQ. This one, the N here being your number density, okay? And then V here being your speed. You see from this first equation to the final equation, your V is gone and is replaced with a term containing N. So the only equation you know that contains number density and contains V here is this one. I is equals to AN QV. So you make V the subject, then you substitute inside here. Okay, you substitute it inside here, and then you eventually get this expression. But I think I better just do it one by one for you, just so you know what I'm talking about. So initially VH is BVD, then you know I is equals to ANQV. So V is I over ANQ. So you sub this inside here, you get VH equals to B I over ANQ D. Now this area here can be re-expressed to become dt and qd, where d will cancel off, so you get back vh equals to bi over ntq. Now there are a few things here that I need to mention to you. What is this a, what is this d, what is this t? Now the a here is the area perpendicular to current flow. The d here is the distance between the charge faces, and then the t here is the length parallel to magnetic field. Okay, now this a here is this a here. In the context of your AS, where you say I is equals to ANQV, where you say that you have a range of particles moving with speed v, your I equals to ANQV. The A here refers to the area perpendicular to your current flow. You say that you have current I moving this way, and the current I is constituted by charged particles moving this way with average drift velocity v, right? Your A here was the area perpendicular to current flow. Okay, so in the context of your semiconductor, in the context of your slice here, your area is actually this part. This is your area. Okay, this one is your area. Okay, it's perpendicular to your current flow, and your area here is actually dt. Your d here is actually the distance between your charge faces. This face is charge positive, this face is charge negative. The distance between them is d. And then this t here, which is your thickness, you notice is actually parallel to your magnetic field. Okay, so this t here is very important to know, because a lot of the times when you do your question, they will ask you to identify which of the given lengths is actually t. So the key here is to look at which length is actually parallel to your field. The length parallel to the field is actually your t. Okay, so that is what Hall voltage actually is. Okay, you derive it until it reaches this form of the equation. All right, so this one should be okay. Then after that, there's just one other thing that I need to kind of mention. When you do your Hall voltage questions, there will be some there will be a small mention of holes. Now, what I'll just tell you first is that holes are just positively charged empty spaces that move in the opposite direction to electrons. That is what I can just mention to you first. All right. So when you do your hole voltage questions and they mention to you about holes, just know this now. Holes are just empty space with positive charge and move in the opposite direction to electrons. Okay. So far so good with this. This one, because if I want to explain this in full detail, I think it will take up to 10 or 15 minutes. I need a question to explain this. Here, I don't have that question, so I can't really explain it in full. So I'll just tell you just to remember this first. When you talk about holes, it's positively charged and it's moving in the opposite direction to your electrons. Okay. Now, the other thing I want to tell you here is this. Now, usually, this is the last thing I just need to mention to you guys now before I can end this. Now, to measure, you know that to measure B, you need to measure VH, right? So when measuring B using VH, the VH should be as large as possible. Okay, when measuring your flux density using Hall voltage, you want your Hall voltage to be as large as possible. Okay, so from the equation, VH equals to BI over NTQ. This one I don't think is really written in your notes, but I still need to explain it anyway. Now, how do you get VH as large as possible? Now, to get VH as large as possible, you can make use of the equation VH equals to BI over NTQ. Now, when VH is large, what must be the corresponding quantities? The B must be large, the I must be large, the N must be small, the T must be small, and the Q must be small. To get a large Hall voltage, B and I must be large, N, T, and Q must be small. Okay, a lot of times in your question later on, when you do it, you notice that they'll ask you what are the ways in which you can make Hall voltage larger. The ways to make your Hall voltage larger, most of the time they will tell you these are the two common ways. You use a different material with smaller number density, like semiconductor, or you just change the slice so that it is thinner. So eventually when you do the question, you will notice these are the things that they like to ask. How do you make your Hall voltage as large as possible? The common thing they'll ask you is you use different material. Different material here as in you use semiconductor with smaller number density. Because for your slice here, you can make use of conductor or you can make use of semiconductor. But the preference is to use semiconductor because number density of semiconductor is less. Conductor, the number density is large, so it's going to cause your Hall voltage to become very small. So normally this is not preferred. They prefer semiconductor. So one of the suggestion is use semiconductor because number density is less. Another thing here is you make sure that the slice here has more thickness. Okay, so that is one way of making sure your Hall voltage is smaller. Another way of making sure your Hall voltage is as large as possible is making sure the slice is perpendicular to your magnetic field. Okay, so this one here, I'll make use of this little diagram here. If this one, I view it from the side like this, I have my current here, and then I have my B here. Okay, now I know that my phases here will be charged. Okay, This is how my Hall voltage is developed. So the one thing that I will tell you first here is that if your slice is perpendicular to your field, your VH is max. Okay. If say you rotate it 90 degrees, where your slice is now like this, your B is like this, and your I is like this, your Hall voltage here is 0. Okay. Then after that, if you say you rotate it 90 degrees again, essentially you rotating it 180 degrees, what you get here is this. Let me just use a different. What you get here is this. Your B is still like this, but your I is now moving in opposite direction. Now in this case, your slice is still perpendicular to the field, but it's just that now it's in the opposite direction, right? So over here, we'll say VH is max also, but opposite polarity. Okay, so why must slice be perpendicular to field? Okay, now the reason why your slice needs to be perpendicular to the field is so that FB is max. When FB is max, there is max accumulation of charges on the faces. So there is larger PD across the faces, therefore larger resulting Hall voltage. Okay. Remember just now I told you when you're talking about the magnetic force acting on a charged particle for wire, I think I told you that if your wire is perpendicular to your field, your magnetic force is going to be maximum. But if it's parallel to your field, your magnetic force is going to be 0. You can apply the same concept for charged particles also. If your charged particle is moving perpendicular to the field, your magnetic force is maximum. If your charged particle is moving parallel to the field, like this case here, you do not have magnetic force. Okay, your magnetic force is 0. So for this case here, where your current is moving parallel to the field, your charged particles is actually not experiencing any magnetic force. You're not going to experience any deflection. You're not going to have any accumulation of charges. You're not going to have your Hall voltage. But if you have it perpendicular to your field, you're going to have maximum magnetic force. You're going to have maximum deflection, maximum accumulation of charges on the faces. You're going to have larger PD. So you're going to have larger resulting VH. Easy way of understanding why I said that is this now. You see, if say for example, your charged particle has FB of say 5 Newton, this isn't the maximum magnetic force. In order for you to achieve Hall voltage, your Fe will need to be 5 Newton also, right? In order for you to achieve Hall voltage. But you say this maximum force, this one is not yet the maximum force. Your maximum force is 10 Newton. If you want to achieve Hall voltage, that would mean that your electric force would also need to increase to 10 Newton. But the only way your electric force can increase to 10 Newton is if there is more charges accumulating. Only then can your electric force increase further. That's why I say here, if your magnetic force is maximum, you're gonna end up with larger accumulation of charges. I think I better write here. Because larger Fe is required. So when you have larger electric force required to balance your larger magnetic force, you're going to need more charges accumulating here. So when you need to have more charges accumulating here, you're going to end up with larger PD, which in turn cause you to have larger resulting Hall voltage. Okay, so that's the gist of Hall voltage here. Now this part here, which explains why must the slice be perpendicular to the field, this one is not a past year question. It's just for your understanding. The thing that they want you to know is that if you want to have large Hall voltage as large as possible, how should the slice be oriented to with respect to the magnetic field? Just know that if the slice is perpendicular to the field, your Hall voltage will always be max. If it is parallel to the field, it will be 0. If it's somewhere in between perpendicular to parallel, your Hall voltage is going to be somewhere in between 0 and max. That's all. Okay. So you have a thin rectangular slice of aluminum with sides of length 65, 50, and 0.1 millimeter. Some of the corners of the slice are labeled. You have a current of I of 3.8 ampere that is normal to phases R, X, XY of the slice. In aluminum, the number of free electrons per unit volume is 6 times 10 power 28. The uniform magnetic field of magnetic flux density B is equal to 0.1 Tesla, is normal to phase QRYZ of the aluminum slice in direction for Q to P. A Hall voltage is developed across the slice and is given by this expression where VH is equal to PI over NTQ. Okay, so this is the Hall voltage equation that just now we were talking about. So we went through the derivation for this. They now gave you that same equation over here. They ask you, use the figure to state the magnitude of distance T. So this T here, I mentioned, is your thickness. Okay, it will always be parallel to the direction of your magnetic field. Okay, so what is the value of your T here? You had been given 3 different lengths here. You have 65 millimeter, 50 millimeter, and 0.1 millimeter. The one that is actually parallel to your magnetic field is actually this one.
10. Yep, 10
yeah, so it's 0.1 millimeter. Okay, so that's the easy way to know what is actually T here. Then the next one, calculate the magnitude of the Hall voltage. So you just use the equation as it is. VH is equals to VI over NTQ. B is 0.13, I is 0.3, I is 3.8, N is 6 times 10 power 28, T is 0.1 times 10 power 3 minus 3, and then Q is 1.6 times 10 power minus 19. This one, why do I use 1.6 times 10 power minus 19? Is because this one is charge of electron.
Yep.
Right? So that one is okay.
For Q, do we always just use the speed of electron? I mean the charge of electron?
Yes.
Okay.
Okay, you will always use that. They tell you this. Because this N here is referring to number density of it's referring to number density is referring to number of free electrons per unit charge. Sorry, number of free electrons per unit volume. So this one is referring to number of electrons per unit volume. The charge that you use ought to be charge of electron. Okay. Right. It will always be charge of electron. Okay. Okay. So this one was the first instance when they tested you on Hall voltage. They gave you something very easy to work with. Okay, so this one is okay. Then after that, you look at page 8. Page 8 again is also your Hall voltage. It's about Hall voltage. So you look at the question little, they will tell you that a magnetic field of flux density B is normal to phases PQRS of a slice of conducting material, as shown in figure 9.1. The current I in the slice is normal to phase QRZY of the slice. The Hall voltage across the slice is given by this expression where VH is PI over NTQ. So state 1 is represented by the symbol N. So as I mentioned to you, it's actually number density of your charge carriers. Or you can actually say number density of free electrons now. Or if you want to be even more specific, you can just say it's number per unit volume of charge carriers or free electrons. Okay. yeah, just be mindful. If you write number density, please try to avoid just writing it as number density alone. You should explain a bit more what is it. Number density of charge carriers or number density of free electrons. Okay. When I mention n, I always just say it's number density lah. It's something like a short form. But when you're asked to define the symbol, you probably should write a bit more to elaborate on what number density actually is. Okay. Yeah, another thing here is that when you say n is number density of electrons or number per unit volume, number per unit volume of electrons, please make sure you mention of the term free electrons. Okay, because when you're talking about the molecular structure of any material, there is actually fixed electrons and free electrons. Fixed electrons are the ones that are constrained to orbit around your nucleus. They cannot move anywhere. Free electrons can actually move anywhere. Okay, so you have to make something like a distinction between the electrons, free electrons. Okay, because those are responsible for your current flow. Okay, now number 2, the symbol T represents the length of one side of the slice. Use letters from figure 9.1 to identify T. Which of the lengths from the diagram here would actually represent T? So as I mentioned, T is thickness. It will always be parallel to the direction of your magnetic field. So magnetic field is here. The length that you can talk about is Px, Qy, or Rz. Any one of this. Okay? Right, so that one is okay. Now in general, Hall voltage is produced in the Hall voltage produced in a slice of metal is very small. For a slice of the same dimensions with same current and magnetic flux density, the Hall voltage produced in a semiconductor is very much larger. Explain why is it that Hall voltage in the semiconductor is larger? So originally they say that the Hall voltage for metal is small. But why is it that when I use a semiconductor, the Hall voltage is going to be large? So one of the reasons is because I mentioned to you earlier that semiconductors tend to have less free electrons, so it tends to have less number density. And because of how the equation or Hall voltage is, where we say to you VH is VI over NTQ, assuming that everything else is the same, VH is actually inversely proportional to N. For semiconductors, N is much smaller, therefore your Hall voltage is much larger.
Okay.
Okay. Right. Okay. Same dimensions here actually refer to same size, length, thickness, or width. Okay. It actually refers to the physical measurements of your object. When you see same dimension, it just basically means same size, same length, same thickness, same width. All right. So that is what dimensions mean. Okay, so that one is okay. Then after that, we move on to the next part. Okay, page 16. Wait, page 16 is this one. All right, okay, so have a look at page 16. We go on to the next question. Page 16, June 17, P42. June 17, P42 is again on Hall voltage or probe. Okay, this one is this one. Okay, right. They tell you a Hall probe is placed near one end of a current carrying solenoid as shown. The probe is rotated about axis XY and then is held in a position so that the Hall voltage is maximum. Explain why a Hall probe is made out of thin slice of material. Okay, now when you first look at this question here, your Hall probe is this one. Okay, your Hall probe is this one here. All right, your semiconductor slice or your conductor slice is actually this little part here, inside here. Okay, So now they tell you that they put your hole probe near a current carrying solenoid. So earlier when we went through the topic of magnetic field, we mentioned that when your current flows through a solenoid, it produces a magnetic field, right?
Yes.
The magnetic field looks like that of a bar magnet, right? Okay, so let's just say that the magnetic field now looks like this now. When you place your hole probe near the solenoid, you are actually trying to measure the flux density or the field strength of the magnet. Okay, that's what is happening right now.
Yeah.
They're asking you to explain why is it that the hole probe is made for a thin slice of material. Okay, so just now I explained to you, you want to have as large of a value of hole voltage as possible during your measurements. So one way to do that would be to have a small number density. Another way to have that is also to have a small value of T. Okay, so here hole voltage depends on thickness T of slice. A thinner slice will cause a larger hole voltage. Okay, so you just need to say the hole voltage actually depends on the thickness of the slice. It's inversely proportional to thickness of slice now, if you want to be even more specific.
Okay.
Yeah. So the thinner the slice, the larger your hole voltage. Okay, then for consistent measure in the next part of the questions, in order for consistent measurements of magnetic flux density to be made, why must the current in the probe be constant? Okay, so in order for consistent measurements of magnetic flux density to be made, why must the current in the probe be constant? Now, just now we know that your hole voltage is Bi over NT cube. Now, in a lot of times, when you try to measure something, your number density won't change because you did not change your material. The thickness of your conducting material will never change. The charge of your electron won't change. The magnetic flux density of the object that you're currently measuring won't change. The only thing that can probably change is your current, right? Okay. You see, when you look at VH equals to BI over NDQ, VH actually depends on current. Okay, when they say in order for consistent measurements of magnetic flux density to be made, why must the current in the probe be constant? The hole voltage inside your hole probe, the hole voltage produced by your hole probe actually depends on current in the slice. So when you measure, you don't want your readings to fluctuate. Okay, when we say consistent measurements, it means your readings do not fluctuate. Okay, you don't want your readings to fluctuate in the first place when you're trying to make some measurements. So we know that your hole voltage actually depends on current. If your current is constant, your hole voltage is unlikely to change. But if your current changes, your hole voltage will change. Okay, so this one will present some problems in the measurements later on. Okay, because ideally when you want to measure something, you don't want the value to change, right? So one of the ways in which you can ensure that whatever you measure doesn't change is you make sure your current is constant right now. Okay. So why must the current in the probe be constant? Because hole voltage depends on current in the slice. If you want, yeah, so you use constant current so the hole voltage remains constant. So the hole voltage remains constant. So because hole voltage depends on current in the slice. That's the reason why we want to make current constant. Okay. All right. So that one is okay. Okay, then we will move on to the next one. Okay, now this one is another one. All right, so they ask you right now, the probe is now rotated through an angle of 360 degrees about axis XY. At angle 0, the hole voltage is maximum value Vmax. On figure 9.2, sketch the variation with angle theta of the hole voltage VH for one complete revolution of the probe about axis XY. Okay, so your graph will look like this. Okay, but why is it like that? Okay, now you can just think of it as this. Now this one here is actually your magnetic field just now. Let me just draw it out properly. This one was your magnetic field just now. This one here was your Hall probe. What you're doing right now is that you are rotating your Hall probe. Okay, your Hall probe is meant to measure the flux density. Okay, so your Hall probe has a certain orientation that you need to follow. You see, just now when we're talking about the Hall probe contains a rectangular slice or conducting material, which looks like this, right? Okay, so the thing here is that one of the things that you need to be aware of is that when slice is perpendicular to B field, when slice is perpendicular to B field, VH is max. When slice is parallel to B field, VH is 0. Okay, yeah. VH is 0. And then the third thing to note here is that when slice is perpendicular to B field, but is, how to say, after being rotated by 180 degrees, when slice is perpendicular to B field after being rotated 180 degrees from case 1, VH is still maximum. VH is maximum, but negative polarity. Okay, now whole voltage is voltage. Now voltage can be positive or negative values. All right, so one thing that I just need to mention to you here is that I mentioned to you earlier that your whole voltage, you aim to get as high of a value as possible for whole voltage. So one of the ways in which you can get a maximum value for whole voltage is by using smaller thickness, using smaller number density. Another way in which you can also produce a larger Hall voltage is by changing the orientation of your Hall probe with respect to your magnetic field. Okay, so what we'll tell you is that when your slice is perpendicular to your B field, your Hall voltage is max. When your slice is parallel to the field, your Hall voltage is 0. But when your slice is perpendicular to your B field, after being rotated 180 degrees from 1 here, your Hall voltage is also max, but you have negative polarity. Okay, it's because you're here for number 3, you're having the opposite face facing the magnetic field right now. It's a bit like, yeah, okay. So that's just one thing to mention here, okay? Right, because
Okay.
you need to know this in order to be able to do this graph here. Basically, what they're saying here is that this is your Hall probe. They are trying to rotate it 360 degrees right now, or 180 degrees right now. Yeah, they're saying that they're trying to rotate 360 degrees. They ask you to show the variation of the Hall probe with the rotation. Okay, so just now they mentioned that an angle of 0 degrees, your Hall voltage has maximum value of Vmax. Then after that, they start rotating your Hall probe. So at 0, you have Vmax. Now, if you rotate it by 90 degrees, your hall voltage will be 0. Yeah, I forgot to write it here. When your slice is parallel to B field, after rotating 90 degrees from 1, your slice will be parallel to your B field. How do I see this? It's basically like this now. I try to draw it out now. Okay. This one will be say like this. This one is my current I. This one is my B field. This one is where I have VH max. Then after that, when I rotate 90 degrees, my hall probe looks like this now. My current is this. This one, my VH is 0. Then after that, if I rotate it 90 degrees again, it will look like this, but my current is opposite. This one is I rotate like this now, counterclockwise now. Okay, so this one is my I, this one is my B, this one my VH is max, but negative polarity.
Okay.
So basically right now, at 0 degrees, we are at this location. I'm having maximum hall voltage. But then once I rotate 90 degrees, I am now at this location. You see it's parallel to my magnetic field, right? So it is 0. Then after that, if I were to rotate 90 degrees again,
Becomes maximum, but in the other direction.
yeah, but maximum in the opposite direction. Okay, because you see my current direction is actually now opposite, you see, right? Then after that, if I rotate 90 degrees again, I will actually get back to this one. This one, if I rotate 90 degrees again, I will actually get back to this location. So this one again is going to be 0. And then after that, again rotate 90 degrees. I'm going to get back to the same orientation as before. So I'm going to get maximum hall voltage, the same as before. So I have these 3 points here. 1, 2, 3, 4, 5. So from here, once you've identified those 5 points, just don't draw a straight line. It's usually a curve. Okay, so just draw a curve like this, sinusoidal curve.
Okay.
Right. So that one will be your hall voltage. Okay, this one is November 17 P41. All right. So this one is actually asking you to describe how hall voltage is actually produced. Let me just open it up. Okay, so this one is which question? Should be wait. November 17 P41. Sorry, I opened the wrong one. Question 8. Okay, question 8. Right, they tell you there's a thin slice of semiconducting material that is placed normal to the field, the uniform magnetic field of flux density B as shown. The field is normal to phases C, D, E, F, which is this top face here, and phases P, Q, R, S, which is the bottom face. The current I passes through the slice and is normal to the phases C, D, Q, P, and F, E, R, S. Basically, it's talking about it being perpendicular to the front face as well as the back face here. They tell you that potential difference hall voltage is developed across the slice when you let current run through the conducting material that is inside a magnetic field. State the phases between which hall voltage is developed. Okay, so this one, your hall voltage is developed across the phases where charges accumulate. Okay, if you refer back to the notes, that time we mentioned that as your charge moves inside the magnetic field, it will be deflected to one particular phase. It will cause that phase to become positively charged, and then the opposing phase will become negatively charged. So across those phases, you have your whole voltage. Okay, you have a voltage across them, you have an electric field across them. So you can actually say that your whole voltage is actually developed across the phases where the charges accumulate. So your role here is to find out where does the charge actually accumulate in the first place. So since this is current, conventional current, you can just take this as flow of positive charge moving in this direction. So I have positive charge that is moving in this direction. This is my direction of velocity. This is also the direction of my conventional current. But since my magnetic field is going downwards, so if I use Fleming's left-hand rule, FBI, I going towards the bottom face there and then B going downwards, you will be able to determine from Fleming's left-hand rule the magnetic force. Your
So
magnetic force,
to the left.
yeah, it's towards this side here.
Okay.
Okay, it's towards this side here. So this side will become positively charged. This side will become negatively charged. So these are the two phases that, between which you will have your whole voltage. So it's just CFSP and DERQ, just like that. All right. Then after that, they tell you the current I is produced by charge carriers. Each of the charge plus Q is moving at the speed v in the direction of the current. The number density of the charge carriers is n. Derive an expression relating whole voltage VH to VB and D, where D is one of the dimensions of the slice. Okay, so this one, they're actually just asking you to find out expressions for VH in terms of these three variables for the time being. So you know that when whole voltage is established, your charged particles will actually just move straight through undeflected. That is one of the main characteristics of whole voltage being established. So once whole voltage is established, your charged particles will actually just move straight through undeflected. So at that time, your magnetic force will be equal and opposite to your electric force that would be developed after you started to have charges accumulating on the faces. So FB equals to FE, FB is PQV, FE is EQ. The Q will cancel each other off, eventually giving you
PV.
your BV. So that's one part. Okay, then also you know that electric field strength is actually whole voltage divided by distance. Okay, so we know that VH is the PD developed across the phases where the charges accumulate. D is the distance between the phases where charges accumulate. Okay, so if anything, well, just now we said that this part here was going to have a whole voltage of say VH, you see, across this slice here, across these two phases here, is where you're going to have your whole voltage. This is also your distance D. Right? So your electric field strength is actually just the voltage across divided by the distance across. So then you sub this one in, you sub in for E, you are eventually going to get VH equals to BVD. This is the first step in the derivation of your whole voltage. It usually involves two steps. The one you see in your notes under page 11, this left side here is your first step. The second step is on the right side. So they only need you to derive the first step first. So you get VH equals to BVD, just like that. Okay, then from there, in the next part, that is where they will start to ask you to derive the full form of the whole voltage. They ask you to use your answer in the previous part and an expression for current in the slides to derive the expression BI over VH is equals to VI over NTQ. So from there, you need to make use of your drift velocity equation that you've learned in your AS. That one is actually I equals to ANQV. So from here, you make V the subject. V is I over A and Q. The original equation was VH over VH equals to BVD. You want to sub V equals to I over NAQ into this one.
Okay.
Right? Then after that, another subsequent thing that you could probably do, I mean, you can just substitute it straight away, right? You can just substitute it straight away. I'll just write at the top right hand corner, VH is equals to B I over A and Q times VV. And then after that, you can also further change some of the stuff here, where you say BI over, sorry, this is not supposed to be a B here, this one is supposed to be a D. Okay, so this one you further substitute it again, you get dt nq times with d. The d will cancel off, giving you bi over ntq. So this one will be shown. So in the derivation in the last lesson, I mentioned to you that A area is the area perpendicular to current flow. And in general, is A is equals to D times T. Okay, where T is thickness parallel to the B field. So in the context of your current question here, the area that you're really looking at is this one. Let me highlight it in red for you. The area that you're looking at is this portion here. This is the area perpendicular to your current flow. You know that earlier in the question, this one is D. This is the distance across the faces where charges accumulate. Your T is actually just the length that is parallel to your B field. So I can say that A is equals to dt. Okay, so that's how I actually got this the expression here. Okay, right. So that one should be okay, right? What I just written in pencil there is just another different way of doing the same thing lah. Instead of substituting for A, I just substitute for D. It's actually something like an extra step. I don't think this one is actually that good. The one that I just wrote in pink here is actually, I think, more straightforward to see. Okay. Right. Is it okay? Okay, so if you're okay, then I move on a little to
I'm still copying.
oh, okay, right.
Yeah.
All right, no worries. So just copy the ones that is relevant.
Jeff, the first point is VH is PV, right? Potential difference. PD, is it?
You mean the one on the right hand side here?
Yes.
VH is PD developed across the faces where charges accumulate. Okay. This one here is VH. VH is the PD developed across the faces where charges accumulate. That is what I wrote there. Wait now. D is the distance between the faces. Between the faces, where charges accumulate.
Okay. A equals to dt where it is what? For the third point.
Oh, you mean this one?
Yes.
Oh, wait, not this one. Right, this one here is
No. The third point on the right. That
oh,
is written in green.
the third one.
Yeah.
A is
A
the
equals
area perpendicular,
regular. Yep. And then the bottom A equals to dt where it is.
where T is the thickness parallel to
Oh,
B
okay.
field.
Okay.
Where T is the thickness parallel to B field. Okay. Where B is the thickness parallel to B field.
Okay, got it. Done.
Okay, right. So that one is all right. Okay, now C suggests why hole voltage is difficult to detect in a thin slice of copper. Why is it that it is difficult to detect hole voltage in a thin slice of copper? Right. So hole voltage actually depends on number of things. From here, you can see that if T is small, VH is going to be large. And then if N is small, your VH is going to be large. So these were the two main things that kind of affect your hole voltage. But the question already mentioned your copper slice is thin, so you can't really mention anything about it being thin, because if it's thin, by right, your hole voltage should be large. But since they're saying it is still difficult to detect it, you can't talk anything about the thickness. You shouldn't be talking anything about the thickness. Instead, you should be talking more about the number density. Okay, because it's copper, we know it's a metal. So metals like copper have number density that is very large. If we have N being very large, your VH would be very small. Okay, so from VH equals to BI over NTQ, if N is large, your hole voltage will be small. That's why it's difficult to detect. Okay, right. Okay, so that one is okay. Then after that, the next one should be page 20. Right. Okay, so next one we can go through is page 20. Right, so I'll move on to page 20 then. Okay, right. Okay, page 20, this one will talk about something similar. This is November 17 P42. Okay, now the first part of the question you will notice is kind of like exactly the same question. I mean, if you just look at the first part of the question. Wait, let me see what question number is this. Is question 8. The first part of the question, the diagram, and then part B1, sorry, part A, that one is actually the exact same question as the one that you've done before. Right? You see this question here that this current question here in page 20, this entire part is actually similar to the previous question that you did under page 18, if I'm not mistaken. We were doing page 18, now we're at page 20. This question here, this part was similar to page 18. All right. Okay, so they ask you to state the phases between which the Hall voltage is developed. So we already know it is DERQ and CFST. It's exactly the same diagram, exactly the same labeling. So this one, I think we can just skip this one. Okay, now the one that is actually different is actually part 2. Okay. So part 2, they want you to explain why a constant Hall voltage is developed between the phases you have named in 1. Why is a Hall voltage developed across the phases in the first place? So just now, to illustrate what we did just now, you have the positive charge. Maybe I should just zoom in a little. Okay, you have a positive charge. It was moving in this direction. This is the direction of your conventional current. And then your B was downwards. So your FB would be here. So your charge particle, your positive charge particle will accumulate on phases CF, SP. This one will be positively charged, the opposing phase will be negatively charged. So what you can do is you can just draw something like this. What color can I use? I'll just use blue color then. This entire phase here will become positively charged, whereas this phase here will become negatively charged. So it's across this phase here that you have your Hall voltage. So how do you explain the Hall voltage being developed? You can actually say that charge carriers moving normal to the magnetic field will experience a magnetic force normal to both current and magnetic field. This is actually 2 points. These charge carriers will accumulate on the faces of the conducting material, which is referring to this phase and this phase. Okay, so we went through it yesterday. We said that as you let the current run, more and more charges will accumulate on the faces. So the charge will build up. So the charge build up sets up an electric field across the slice. And then I also mentioned that as you keep accumulating the charges, your electric force will keep increasing, but it will not increase indefinitely. It will increase up to a point where your Fe is equals to Fp. So at that point, your charge particles will just move straight through. So this is where your Hall voltage is developed. Okay, so back to this one, we say charge builds up, sets up an electric field across the slice. The charge will stop building up when the force due to magnetic field equals to force due to electric field. The voltage across the PD, and the voltage of PD across the slice thus becomes constant. Yeah, there's a typo error here. This one is FB equals to FE. I wrote it as FC. Okay. All right. Can I move on? All right. Okay. So this one is okay. All right. Okay. The next part, the last part of the question, this is where we talk about holes. This is the remaining part of the chapter that I need to no, this one is not yet talking about holes. Sorry. This is actually the next question. Okay, for the last part, part B, two slices have similar dimensions. Dimensions, I say, is mainly the length, the width, the thickness, and so on. One slice is made out of metal and the other slice is made out of semiconducting material. For the same values of flux density and current, state which slice, if either, will give rise to a larger hole voltage. Explain your working, right? So basically, we already know that semiconducting material or semiconductor material will tend to have a larger hole voltage. But how do we see it? We can always look at it from the hole voltage equation. So Bi over NTQ. So here, when we see that they say that you have similar dimensions, T is constant. You also say that you have the same values of flux density and current. So this one means B and I constant. Okay. So, and then after that, you're talking about flow of charge carriers. Q is also constant. A charge carrier is electron, which is always the case when you're talking about a circuit. All right, so Q is also constant. So if B, I, T, and Q is constant, hole voltage is actually inversely proportional to number density of charge carriers. Since semiconductors have lower number density, therefore, hole voltage for semiconductor slice is larger. So VH equals to VI over NTQ, B, I, T, and Q constant. VH is inversely proportional to 1 over N. So N is small, VH is big. This one is the proper explanation in short form. All right, this one is worth 2 marks. Okay, right. Okay, so this one is okay. Then after that, there's I think page 23. Wait, voltage 18, 20, 24, 23. Okay, the next one, page 24. Oh, this one is the one that I need to mention with the host. Okay, have a look at page 24. Okay, page 24. This one is March 18 P42. Okay, right. So if we're talking about March 18 P42, question 9. So they give you something like a similar diagram again, but this one, they change the direction of the current, right? Before this, your current was actually going in this direction, but now they go and tell you your electron flow is here, or rather your current flow is over there. All right. Okay, so now same thing as before, we just go through this very quickly. You have a thin slice or conducting material with phasors PQRS and WLBWXY normal to a uniform magnetic field of flux density B. Electrons enter the slice at right angles to phasors SRXY. A PD, which is the hole voltage, is developed between the two faces of the slice. Use the letters from the figure to name the two faces between which hole voltage is developed. Okay, so this one, you have to look at where are the charges being deflected across, where are the charges being deflected to. So the faces, the faces where your charges are accumulating is where you're gonna have your hole voltage. Right, so a key thing to note here is that this is flow of electrons. So you can think of a negative charge as moving in a velocity in this direction, with a velocity in this direction. But since this is flow of negative charge, when we want to use Fleming's left-hand rule, we need to use conventional current, which is the flow of positive charge. So our positive charge is actually going opposite direction. This is our direction of our conventional current. This should be the direction of I. And then our B is downwards. Maybe I better just write it here. And then your B is downwards. If you were to use your Fleming's left-hand rule right now to determine the direction of the magnetic force, I is going towards the right, B is going downwards. Your magnetic force is going to be
Towards QR.
QR. Yes, correct. So write this. This one is your I. This one is your FB. Okay. Right. It's going to be deflected towards faces QR, WX to be specific. Okay, but this is negative charge, you see. So your negative charge is going to be deflected to this face here, negative, 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 negative. Okay, so this is where all your negative charges are. This side will be negative. So the faces opposite to it, which is this one, will therefore be positive. Okay, so your whole voltage is actually developed across these two faces. Okay, this is your whole voltage developed across these two faces. The faces QRWX will be negative, and faces PSVY will be positive. Okay, so they ask you to name the faces. I've just actually named it already. But then after that, the subsequent question will ask you, state and explain which of the two faces is actually the more positive one. Okay, so you know that electron is actually deflected towards faces QRWX, therefore faces PSYV will be positive. Okay, you can actually just write it in your own words if you wanted to. Electrons moving in the magnetic field is deflected towards faces PQXW, therefore it is negatively charged. Thus, the phase PSVY would be positive here. Okay, something like that. Right, so that one is okay.
Okay.
Okay, right. Okay, so that one is okay. Then you move on to the next page. Okay, the whole voltage VH is given by this expression where VH is BI over NTQ. Use the letters in figure 9.1 to identify distance T, the thickness. So thickness T, I mentioned to you, is the length parallel to the direction of the magnetic field. It can be any one of those lengths that you see right over here. It's either going to be PV, SY, or Rx. Okay, Rx as well as QW.
Okay.
One of this. Just choose any one. Okay, so you're gonna get that answer. This is 1 mark. And then after that, state the meaning of the symbol N. And the symbol N is actually number of charge carriers per unit volume. If let's say somehow or another you subconsciously use electron, then it's also correct. But you need to be careful to write this number of free electrons per unit volume. Okay, if you are using the term electrons, you must use the word free. Okay, so that one is okay. Okay, now part 3 relates to what we call a hole. All right, so here they'll tell you, state and explain the effect, if any, on the polarity of the hole voltage when negative charge carriers are replaced with positive charge carriers moving in the same direction towards the slice. Okay, so right now they tell you, instead of having electrons that are the charge carriers, you now have positive charge carriers moving towards the slice. Okay, So this one is actually talking about holes, right? So let me just explain to you a bit about holes. Okay, now they're just telling you that you have positive charge carriers. Okay, so let's just go with this one. You have a look at the notes, page 11.
Okay.
Yeah.
Mhm.
Right. Sometimes when you read through your questions, you will hear mention of something called holes. Okay. Now, holes are just positively charged empty spaces that move in opposite direction to electrons. Okay. So if we ask you, if we mention to you holes, generally this is the thing that we would assume. Holes are positively charged, they carry the opposite charge to electron, and they always move in opposite direction to electrons. Okay, so why do we normally say this is mainly due to something like this. Let's just say, for example, this one is a diagram showing it to you, but I think I better just draw a separate one because it's easier to show it from there. Let's just say right now, I'm looking at a layer of material. I'm looking at a layer of material, which is this one. Okay, and then I look at that same layer of material at different times. Say this one here is t equals to 0, t equals to 1, t equals to 2, and then t equals to 3. Now for that particular layer of material, I have a row of electrons that are negatively charged. Okay, now what if I tell you that at time t equals to 0, this electron here actually move away? Because you have current flow, this electron suddenly move away. So the moment this negative electron move away, what will happen is that the moment the negative charge moves away, you will leave behind an empty space that is positively charged. Okay, so originally at t equals to 0, your electron was here, but then because it started to move away, it suddenly leaves an empty space there, and that space becomes positively charged because you already lost an electron. Okay, so this is at t equals to 1. Now, at t equals to 1, because this one is a positively charged hole, the next instant of time, what will happen is that this electron will now try to move into this spot. So you see that this one now is negative, and then this spot here is positive. Okay, because this one suddenly move into here, this spot becomes negative, this spot becomes positive. Because this spot here, it lost an electron, there's an empty space, and it became positively charged. Then after that, we look at the next instant of time. At the next instant of time, this one wants to go inside here. So what you will see is that this one is negative, 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 and then this one is going to be positive. Sorry, it's the wrong tip. Okay, so this one is positive. Okay, so you will see that later on in the next instant of time, this one will start to move in, and then this one will become positive also, right? Okay, so now you see, if I just let this thing run as it is, you will get the impression that the holes is going in this direction. Because you see, originally it started off here, then it moved to here, and then it moved to here. So the next instant of time, it should be going to here already, right? The holes are going towards the left. But at the same time, you will notice that your electrons were actually going towards the right. Because you see, the electron went here, the electron went here, the electron went here, and the electron also went here, right? It's actually trying to move towards the right. Okay, that's why we normally tell you that holes are positively charged and they always tend to move in the opposite direction to electrons. Okay, that's what holes actually is. All right. The one in your current question here didn't really mention it as holes, they just mention it as positive charge carriers. And at the same time, they tell you that it is actually moving in the same direction towards the slice. Okay, so there's some slight variation here, all right? They didn't really specifically mention to you holes, but it's just something that you need to know because I think there are a few questions that tend to deal with holes. So the fact that they are positively charged and move in opposite directions to electrons is something that you just need to know. Okay, now, so if you look at the answer right now, they tell you, rather than using electrons as the charge carriers, you now have positive charge carriers. What do you suppose will happen to your Hall voltage? Okay, so the answer was just that negative and positive charge carriers will deflect in opposite directions. Phases P, S, V, Y is still more positive, thus there's no change in polarity. Okay, if you just read it as it is, it sounds a bit confusing. It seems like it doesn't make sense. So it will only make sense if I try to draw it out for you. Okay, you see, if I were to just look at the, because right now they say that originally it was your electrons going here, right? All right. And then we tell you that your Hall voltage is developed across these phases. So let's just say right now, I'm look at it from the top. So if I look at it from the top, you see this one. This is how it looks like. Now we know that your electron came in like this. And now I know that your magnetic field is going into the plane of the paper. So when your electron came in here like this is your direction of velocity. Maybe I better just get rid of this one. If your electron was entering like this just now, this is your V, but this one is your I. But this one is your I, and this one is your, sorry, and then your FB is going upwards, right? Like this one is, if I'm looking at the top, I'm looking at this face as it is. And what you're seeing here is you looking at the top, looking at faces PQRS. So we know that your electron will be deflected outwards, thereby causing this edge here to become negative, and then this edge here to become positive, right? That was the conclusion that we found out. Okay, now, if you take what the question mentioned to you, they say that rather than having electrons, negative charge flowing in that direction, what if right now you have positive charges flowing in the same direction? The question here specifically mentioned to you that what if you have charges that move in the same direction, positive charge that move in the same direction? So rather than having a negative electron, you now have a positive charge that moves in the same direction. So this one is the motion of your charged particle moving in the same direction. This is also the direction of your conventional current. Now, if you use Fleming's left-hand rule, where do you suppose is your magnetic force going to be? Is it pointing downwards or upwards? B is going into the plane of the paper, your I is going towards the right. Can you get the magnetic force as downwards? Do you manage to get the magnetic force as pointing in this direction?
Yep.
Okay, so your magnetic force is also, your magnetic force is now pointing in the opposite direction because mainly your charge is oppositely charged right now. But notice that when you go and when you look at the charge itself, positive charge is being deflected downwards. Okay, your positive charge is being pushed downwards. So your side, your bottom face here will actually be positive, whereas your top face will actually be negative, right? Correct? In the first instance, electron was pushed here. So this side will be negative, this side will be positive. In the second instance, positive charge was pushed down here. So this side becomes positive, this side becomes negative. Now, in terms of the polarity of the Hall voltage, do you think there's any change in polarity? We know that this is your Hall voltage. The PD across the phases where charge accumulate is your Hall voltage. Now, looking at this situation right now, does the Hall voltage have different polarity, or are they going to be the same? They should be same polarity, right?
Mm-hmm.
Okay, so different polarity would be where if it has opposite polarity, this one will be positive, this one will be negative. That is what we mean by opposite polarity of your Hall voltage. But the fact is that right now you're seeing the same polarity for both of them. Okay.
Mm-hmm.
Now the charged particles will be deflected in opposite directions, but it doesn't cause your polarity to change. Okay, that's why here you notice the statement is written like this. The negative and positive charges would deflect in opposite directions, which is this one and this one here, but that one doesn't cause any change in polarity. Phases PSVW, YV is still more positive, thus there's no change in polarity. Phases PSYV is actually this bottom portion here. It's actually this phase here.
Mm-hmm.
Okay, so it's actually talking about this one, PSYV. This one is also PSYV. Okay, so no change in the polarity. All right. Okay,
Mm-hmm.
so this one is one part. Then after that, there's one last question here. I think 24. We just did 24. The last one should be 33, I think. 33 is this one. Yeah, we have a short look at page 33, and after that we can probably cover. Okay, page 33. This one relates to graph drawing.
Mm-hmm.
Okay. This one is what year? This one is November 18 P42, question 8 and above. I believe it's 9. Yeah. Okay, let's go with this one.
Mm-hmm.
Right now, you have a hot probe that is placed near one end of a solenoid that has been wound on a soft iron core, as shown in this figure. The current in the solenoid is switched on. The whole probe is rotated until the reading pH on the voltmeter is maximum. The current in the solenoid is then varied, causing the magnetic flux density to change. The variation with time t of the flux density B at the whole probe is as shown. So then they tell you at time t equals to 0, the whole voltage is V0. On figure 9.3, draw a line to show the variation with time t of the whole voltage from 0 to T4. Okay, so basically, this one is a combination of your magnetic field. This one is relating to what you learned in the beginning part of your chapter. This one here is your solenoid. Current is actually flowing through your solenoid like this, going through your coils or wire and then coming back here. So we already know that when current flows through a solenoid, it produces its own magnetic field. So your magnetic field would probably look something like this right now. Okay, and then you put a Hall probe. Your Hall probe, as I mentioned to you, is meant to measure the magnetic flux density B. Okay, so your Hall probe contains that conducting slice, which can be made out of metal, can be made out of semiconductor. Its purpose is to give you what we call a Hall voltage. The Hall voltage is a measure of your flux density B. All right. So here they tell you your Hall probe is rotated in the first place until your voltmeter reading is maximum. So this one is actually telling you that the slice is now perpendicular to the B field. In the last question, in the last lesson, we mentioned the effect of rotating your slice with respect to the magnetic field. If your slice is perpendicular to the B field, your hole voltage is going to be maximum. But your slice is parallel to the B field, your hole voltage is going to be 0. Okay, so here, when you read this one, the slice is already perpendicular to the B field. Okay, this one is at T equals to 0. All right. So right now, what the question wants you to do is that they tell you current is the solenoid is varied, which causes the flux density to change. The B will change with the current right now. The variation with time of the B with time, the variation with time of the flux density B is shown in this graph here. They want you to draw the corresponding hall voltage variation with time. Okay, now before we go to that, some things to note. If B is constant, VH by right should be constant. If B increase, VH should also increase, and vice versa.
Okay.
Okay. The reason why we can say this is because when VH equals to BI over NTQ, we know that VH is actually proportional to B. If B is constant, VH should be constant. If B is increasing, VH should increase. And then if B decreases, VH should also decrease. So your graph should basically look like what you see at the bottom here. It should be something that looks like this. Okay. This one I can see it is constant. This one I can see it is decreasing. And then I also see that this is constant, opposite polarity, and larger magnitude. Right? Yeah, I think I better also mention this. B change direction, VH change direction. Okay, so these are some things to kind of note from there. All right. Yep. Okay, so this is what you can see. If this section here is constant, VH should be constant. If this section here is decreasing linearly, this one should also be decreasing linearly. But then the last part here is where you need to be careful a little. This one is constant, opposite polarity, negative sign, and larger magnitude. So you need to make sure you're doing the same. Constant, opposite polarity, and larger magnitude. Okay, right?